Hi there. In this video, we're going to look at how to expand a complex variable to be in terms of a series. That is, we're going to apply the Maclaurin series expansion to a complex variable. So what these series expansions do is that they take a function in general and they convert it into a sum of infinite terms, and those terms are polynomial terms. So the Maclaurin series is actually a specific case of the Taylor series. The Maclaurin series is applied for a value of x where it's near 0. So we would apply the Maclaurin series for where x is near 0. So where x is near 0. So if we were to write out the Maclaurin series expansion, not just yet for a complex variable, even though it's the same thing, the general series expansion is that f of x is equal to, firstly, where f is equal to 0, so we would substitute 0 in terms of our given function. That would be this term. Then we add to it x, and we multiply it by the first derivative, where x is equal to 0. So we would say x is equal to 0. So we can just write 0 inside here. And then the next term is we would now increase the degree. So x is equal to 1 here, then it's equal to 2. So we have x squared, and then we multiply it by the second derivative, where x is equal to 0, and we divide by 2 factorial, and 2 factorial is just 2. And then next term, we add x cubed, and we would have the third derivative at 0, and we would divide by 3 factorial. So we can carry on adding terms in this fashion here. And then if we were to extend it to the nth term, then what it would look like is x to the power n. You can see that this is the pattern. 1, 2, 3, and then the nth term is just n. And then we would have the derivative of the nth order at 0 and divided by n factorial. And it would carry on like that. So how do we extend this to a complex variable? We would remember that a complex variable z is made up of an x and a y, and it's in the complex plane and all of that. Well, to extend it to a complex variable, it's exactly the same thing. All we would do is we would substitute x with z. So this entire thing would just become a function of z is merely equal to that function where z is equal to 0. Then we would have z, and then we would have first derivative at 0 plus then z squared, then the function second derivative where z is equal to 0, then divided by 2 factorial, then plus z cubed, and then third derivative with 0, then divided by 3 factorial, and so on. And then the general term would be, of course, z to the power n, and then the nth derivative at 0 and divided by n factorial. So the difference here between a function where z and x, we would remember that there are some complications in terms of how we analyze it. Remember that z may have a singular value. Remember that we would think of the Cauchy-Riemann equations and so on. So we're going to get into whether this expansion is actually valid in the upcoming videos and how we interpret the different points where it might or might not be valid. So just to do this for a single example or a simple example, we could have a function. Let's just say where f of z is equal to 1 plus, or rather 1 minus z to the power minus 1. So we want to expand out this function in terms of the Maclaurin series, and the way we would do that is by now computing these various terms. So we would firstly take where first term z is equal to 0. So where z is equal to 0, so we'll just write 0 here. And then this is equal to 1 minus 0 to the power minus 1. And this is just equal to 1. And then now we take the first derivative. And this is 1 minus z, 1 minus z to the power minus 2. Minus 1 will come to the front, okay, and we subtract 1. So minus 1 becomes minus 2. And then we take the derivative of the inside function. So we're actually using the chain rule here. So in the front there's minus 1, and then the inside of the function, the derivative is minus 1 as well. So minus 1 of the inside times minus 1 of the outside gives us just a 1 in front. So it's the same thing here. That's how we get this 1 in front. So now if we compute that first derivative at 0, then we would have 1 minus 0 to the power minus 2, and that again gives us 1. Then we find the second derivative, then we would have minus 2, and then times the inside function minus 1, so it just gives us 2 on the outside, so we have 1 minus z to the power minus 3, and that derivative at 0 is equal to 2 into 1 minus 0 to the minus 3, and we can write that as 2 or 2 factorial. So we carry on in this manner. So we have the third derivative at z. So this minus 3 times this 2 gives us minus 6, then minus 6 times the derivative of the inside, which is minus 1, gives us 6, minus 3 times minus 3 times 2 times minus 1. So that's 6 we're going to write as 3 factorial, and it'll be 1 minus z to the minus 4, and the value of the third derivative at 0 is simply going to be 3 factorial into 1 minus 0 to the minus 4, which is just equal to 3 factorial. So we can see a trend appearing here right now, and we can generalize these terms at this point. So we would have the nth derivative of z is simply equal to n factorial into 1 minus z, and now we have minus n in the exponent, but 1 less than minus n. So you can see that the third derivative here, we have minus 4. So we have to take minus n and subtract 1 from it. So if we find the nth derivative at 0, then we see that it's simply equal to n factorial into 1 minus 0 to the power minus n minus 1, and that just gives us n factorial. So we now substitute these terms into our series expansion. So if we do that, so we just bring this here now down. So we have f of z, and the first term is f of 0. F of 0 is 1. And the second term is z, so we write z. And f prime 0 is 1, so we have to multiply it by 1. And the third term, we have z squared. Then we have the second derivative, and that's equal to 2 factorial. So we have 2 factorial, and we're dividing by 2, or 2 factorial. And the third term, we have z cubed. Then we have the third derivative, at z, with z is equal to 0, which we can see is 3 factorial. And we divide by 3 factorial. So it carries on in this manner, and then we have z to the power n, fn at 0, which we can see is n factorial. Put that in. And we divide by n factorial. So all of these factorial terms will cancel out. They become 1. So what are we left with? We are left with the fact that this series expansion is equal to 1 plus z squared plus z cubed plus then z to the power n, and so on. We need to understand whether this series is actually valid, where it's valid, for what values of z is it valid. So when we're asking about its validity, we're actually asking about its convergence. So we need to check in which ranges of z is it valid, because remember that if we look at our function, our original function, with which we had applied this series expansion for, which is this, we can see that we have a singular point where z is equal to 1. So what does this mean? How do we interpret that, and how do we go about checking in general for the ranges of values of z for which this kind of function is valid. So we're going to talk about that in the upcoming video, and we will talk specifically about the ratio test. Thank you very much for watching.